Have you ever stopped to think about how something like a vending machine or even a simple traffic light just knows what to do next? It's not magic, right? It's memory. But here's the real head-scratcher. How can a bunch of simple on-off switches remember anything at all? Well, let's dive right in, because the answer is this really elegant idea that pretty much powers our entire digital world.
So, this is the big question we're tackling today. How can a circuit, which is really just a collection of switches, remember what happened a second ago? You know, how does it know that you put a nickel in before you put in a dime? That ability to react to a sequence of events, not just what's happening this very instant. That's the whole ballgame.
To get our heads around this, we really need to look at two different kinds of circuits. Over on the left, you've got what are called combinational circuits. Think of a basic calculator. You punch in 2 plus 2, it gives you 4. It only cares about what you're doing right now. It has zero memory of what you did before. But on the right, this is where things get interesting. We have sequential circuits, and their output depends not just on the current input, but on everything that's happened before. They have memory.
And the solution, the way we give these circuits that memory, is this brilliant concept called a finite state machine. You can think of it as the secret ingredient that lets really simple hardware do some incredibly complex step-by-step tasks.
Okay, so finite state machine, or FSM, sounds a little intimidating, I get it. But the idea is actually super simple. Just picture a machine that can only be in a handful of specific conditions or states. It just hangs out in one state until some kind of input comes along, and that input makes it jump or transition to a different state. And that's basically it. It's just a way to map out behavior based on a limited number of states and the rules for jumping between them.
Let's break it down into its building blocks. Every FSM has a few key parts. First, you've got the states. These are like the machine's memory of what's happened so far. For example, a state could be waiting for a coin. Then you have inputs. These are the events that trigger a change, like you actually putting a coin in. Those inputs cause transitions, which are just the rules that say, hey, if this happens, go from this state to that state. And finally, you have outputs, which are the actions the machine performs, like, actually giving you your can of soda.
So, how do engineers actually go about building one of these things? I mean, it's not just a cool theory. There's a really clear, structured process for turning a logical idea into a physical working circuit. It's all about going from a concept to actual hardware.
And that design process really comes down to 3 main steps. First, you draw up a state diagram. This is like the visual blueprint for how the whole thing is supposed to behave. Second, you take that visual map and you turn it into a state table, which is just a way of writing down all the rules in a formal, organized chart. And then finally, that table becomes the guide for building the actual physical circuit out of basic electronic parts called logic gates.
So here's what a super basic state diagram looks like. Each one of those circles is a state. Let's imagine state A is off and state B is on. The arrows, those are the transitions. So this little map is telling us, if we're in state A, which is off, and we get an input of 1, we follow the arrow over to state B, which is on. And if we're in state B and get an input of 0, we just follow the arrow right back to state A. See, we've just visually mapped out the entire logic of a simple on-off switch. The next logical step is to turn that diagram into a state table. This is just a really clean, organized way of writing down those rules we just drew. The first row here says, if our current state is A and the input is 1, then our next state is going to be B. The second row says, if our current state is B and the input is 0, our next state is A. This table is basically the direct instruction manual we'll use to build the circuit.
And here it is, the proof that it all actually works. This is a simulation, a timing diagram that shows our FSM in action. That line labeled Y is the machine's current state. You can see it starts in state A. Then, when the input W changes, boom, the state transitions to B and then later to C, all perfectly in sync with our rules. This simulation is so important. It lets designers check that their logic is perfect before they ever build a single piece of hardware.
Okay, so that's all the theory, but I know it can feel a little abstract. So let's bring it back down to earth with a perfect real-world example that we all know, the humble vending machine. Because believe it or not, the entire brain of that machine is just a finite state machine. So let's set the scene. We've got a really simple vending machine. It only takes nickels and dimes, and everything costs 15 cents. The big question is, how does it keep track of the money you've put in?
Right, so the machine's brain has a few jobs. It has to remember the total amount of money it's received. It has to know when that total hits 15 cents, and then it has to do the right thing, dispense the item. So how does it remember? Well, the amount of money it's holding right now is its current state. The memory is literally baked right into the definition of each state.
Let's just walk through the logic. The machine starts in its idle state, right? It has 0 cents. You walk up and put in a nickel. Click. It transitions to the 5-cent state. Now it's just sitting there, waiting. Then you put in a dime. Click. It instantly jumps to the 15-cent state, and its output, its action, is to dispense your item. What if you put the diamond in first? No problem. It would just go to a 10-cent state and patiently wait for you to put in a nickel. Every single combination of coins just guides it down a pre-planned path from one state to the next.
And of course, this simple vending machine logic, it's really just the tip of the iceberg. Finite state machines are the unseen engine humming away behind countless devices we use every single day, managing all sorts of sequences and controlling how things work.
So what's the big takeaway from all this? Well, it's that finite state machines are this beautiful framework for giving simple circuits the power of memory. And with a really straightforward design process, diagram to table to circuit, engineers can turn abstract logic into reliable hardware. These things are the hidden brains running our world, inside everything from traffic lights and elevators to the digital clock on your oven.
And that kind of brings us to the final thought. When you think about it, from unlocking your phone to using an ATM to just waiting at a crosswalk for the light to change, you are interacting with these little logical engines all day long. So the real question isn't if you've used a finite state machine today, it's how many can you even count?